Hyperspectral imaging systems aim to capture the full spectral information of a scene in some band of the spectrum. They have applications in crop and environmental monitoring, mining, and other machine vision tasks. As these systems are often highly specialized and difficult to produce, they can cost tens of thousands to hundreds of thousands of dollars. However, making these systems more readily available could open up many more applications in research and smaller scale operations. Consequently, there is significant research into low-cost hyperspectral imaging systems. In the paper Compact Single-Shot Hyperspectral Imaging Using a Prism, published in 2017, researchers from CASE, South Korea, and the University of Zaragoza, Spain, present a hyperspectral imaging system which uses only a consumer RGB camera and a glass prism to reconstruct a full visible band hyperspectral image. Their model allows for high-resolution hyperspectral imaging at very low cost. The idea behind the approach is to use the dispersion from a prism mounted in front of the camera's lens to provide hyperspectral information on a scene. Using the observation that hyperspectral information is visible in dispersion at edges in the image, the reconstruction procedure consists of locating the edges in the image, then applying information about the edges to reconstruct the full hyperspectral image. Before we can start solving for a hyperspectral image, we first need an image formation model. We want to know where light from our scene ends up on our sensor and how it relates back to the hyperspectral image we're trying to reconstruct. To do this, we'll start with a basic pinhole camera which models our camera without the prism. The pinhole camera model simply accepts light from the scene through a single point and captures it on its sensor. To model this, we draw a line from a point in the scene Q to the corresponding point on the sensor, PD. Now, adding the prism, light is diffracted based on its wavelength, causing the image formed by a point in the scene to be dispersed on the sensor. To formalize this model, we need to start defining some terms. For a ray of light with some wavelength lambda, at some pixel p lambda on the sensor, we want to know how dispersed it is from some other ray coming from the same point in the scene Q with a reference wavelength lambda ref. To do this, we will also define a reference pixel p lambda ref and a base non-refracted pixel pd. We start by finding theta lambda, which maps the point p lambda on the sensor to a point in the scene Q with some depth z. Then, using theta lambda, we define psi lambda, which maps from p lambda to the non-refracted pixel pd. From this, we can relate p lambda and p lambda ref by defining phi lambda, which maps from p lambda ref to p lambda using psi lambda ref and psi lambda inverse. We can then define the dispersion as p lambda minus p lambda ref. Applying the dispersion magnitude over depth shows that the dispersion's dependence on depth quickly vanishes as the depth increases. This allows us to set z as fixed and define dispersion in terms of only wavelength and pixel location. Our image formation model can now be defined as j equals omega phi I, where j is the dispersed RGB image, I is the hyperspectral image, and phi and omega describe the dispersion in hyperspectral to RGB operators. Now that we've defined our formation model, we begin to reconstruct our non-dispersed image. To do this, we start by finding edges in the image. The dispersion adds a lot of blur, making it difficult to find edges currently, so we need to restore the edges first. This is done by finding a base hyperspectral image, I-aligned, which could reasonably result in the RGB image observed by our camera. This search problem is solved using a gradient descent method. This results in an aligned image with sharp edges. Now we can apply an edge detector to find areas where dispersion could be observed. While I-aligned does contain hyperspectral information, it is nowhere close to being accurate. To address this, we need to include information about the edges into the reconstruction algorithm. To do this, we start by reconstructing the spatial gradients of the image, g hat, then reconstruct the hyperspectral image, I opt. This is done with another two optimization steps. Finding the spatial gradients involves a similar minimization problem as doing alignment. However, finding I opt is more complex. The loss function for I opt incorporates information about the edges of the image to decide what information is relevant to the optimization. This is done with a confidence matrix, which assigns the confidence to each pixel, weighting the influences on the loss function. Observing the results, the reconstruction is quite close to the ground truth spectra of the image. Compared to other systems, the model also does quite well, with significantly higher spatial resolution than the other systems. The system does have some drawbacks, however. It requires well-defined edges throughout the image for accurate reconstruction. Additionally, performance degrades when edges are close to one another, and high-frequency spectral details like those created by fluorescent lighting decrease the system's accuracy. In conclusion, this paper presented an elegant single-shot hyperspectral imaging system. The system's low cost and single-shot nature makes it good for casual hyperspectral photography, enabling general use. Thank you for watching. For further reading, all sources can be found in the description.